It looks like there is some difficulty in understanding when I introduce synthetic antiferromagnetism. So let me explain again. So your normal in-plane MRAM as a free layer, magnesium oxide, a reference layer, which is spinned along certain direction by antiferromagnetic layer. Okay, so this is the normal in plane MTJ. Okay, so when I introduce synthetic antiferromagnetism, you are getting confused. Okay, so synthetic antiferromagnetism based MRAM also has everything similar. So we have a free layer, you have magnesium oxide, okay, you have a reference layer, then you have a AFM layer. Okay, the only difference between the SAF structure and the normal in-plane MTJ is that this reference layer doesn't have one layer. So here we have only one reference layer. Okay, so in the case of synthetic antiferromagnetism concept, this reference layer is made of 3 layers. Okay, so the bottom layer of the synthetic antiferromagnetic structure is spinned by the AFM, so it will be along this direction. Then you have ruthenium or iridium to induce the antiferromagnetic coupling. Okay, so instead of one layer, you have 3 layers. Okay, so your reference layer is like this. This whole thing is the reference layer. So when you read information, what matters is the top ferromagnetic layer. Okay. Okay, so your top magnetization of the reference layer is along this direction. So if free layer is parallel to that, you will have low resistance. If your free layer is anti-parallel to the top layer magnetization, you will have high resistance. Okay. So when you are talking about reading, we are talking about, let's say this is the magnesium oxide, this is free layer. So we are only talking about this layer.
Why do we need to close the stray fields? That's a very unique case.
Yeah, why do we need to close the stray field? Is because otherwise, you know that this is the like north pole of a magnet, south pole of a magnet, right? This field is coming and influencing the free layer magnetization. Okay, so if there's a magnetic field, so this direction will be favored. Okay, whereas free layer magnetization in the other direction. This is not favored. Okay, this is like having two north poles parallel to each other.
Then also, yeah, you took H equals to 4 pi ms
Mm.
for thin films.
Mm.
So, what constitutes such thin film? I mean, how far you can stretch this formula for bulk materials?
For bulk material, let's say you have a, okay, this is coming from the shape anisotropy. So you look at the concept that we learned about demagnetizing field in the magnetism chapter. So when I introduce the stray field, not stray field, shape anisotropy. So when I introduce shape anisotropy, I mentioned that the demagnetizing field is responsible for this shape anisotropy, and this is basically a tensor. So depending on the shape of your object, you have a demagnetizing field tensor. So if your bulk magnet is in spherical shape, this demagnetizing tensor has equal value in all directions because spherical is uniform, right? So if you have a flat object like this, the demagnetizing field is stronger in this direction. Okay, so now let's move on to the next topic, which is about perpendicular MRAM. So as the name implies, let's say this is your wafer, the magnetization will be perpendicular to the wafer plane. So that's perpendicular MRAM. So let's say you have a reference layer pointing in the up direction. Your free layer can be parallel or anti-parallel. That gives rise to state 0 and 1. Okay. So only when we are talking about in plane MRAM, so within the plane magnetization can be in any direction, but out of the plane magnetization is like only either up or down, right? So you don't need a pinning layer in the case of perpendicular MRAM. You don't need a pinning layer. You just make this layer to have a very large coercivity. You can have the free layer to have small coercivity. Okay, so whether you apply magnetic field or spin transfer torque, that current will be only switching the magnetization of this free layer to be parallel or anti-parallel. It won't affect the magnetization of the reference layer because it has a large coercivity. So you don't need the antiferromagnetic materials to pin the magnetization direction. So this is like the concept pseudo spin valve that we learned. So we just make use of some large coercivity material here, so that during the writing operation you only switch the free layer magnetization. Okay, so in this case, if you make a thin film, in the absence of anisotropy, magnetization will lie in plane. But if you have certain material with sufficient anisotropy, then you can point the magnetization to be out of plane. So usually the perpendicular MRAM uses materials with a larger anisotropy. So this anisotropy is needed to make the magnetization point in the perpendicular direction. Okay, so we mentioned that in the case of in-plane MRAM, we spend extra energy to write information, but here we don't have that problem. Okay. So here we have an anisotropy which can lift the magnetization from in-plane to the outer plane direction, right? So if you want to switch, if you want to keep the magnetization in plane, so if you remember the Stoner-Wohlforth case, this is easy direction, and this is the hard direction loop, right? So here we have certain anisotropy in the perpendicular direction. So perpendicular direction is the easy direction, and in plane direction is the hard direction. Okay, so if you want to make the magnetization to be lying parallel to the MRAM, parallel to the wafer, you are just applying a field that's equivalent to HK. Okay, you apply a magnetic field equivalent to HK, then you can tilt the magnetization in the hard direction. Okay, so because of this reason, in the case of perpendicular MRAM, the writing energy and the storing energy are same. Okay, so we have learnt that the energy barrier is coming from anisotropy, right? KUV. Which in other words it will have this formula. Okay, so you don't spend extra energy in writing operation. So we can say that writability in perpendicular MRAM technology doesn't need extra energy to write information. So that is the first advantage. The second advantage is the thermal stability. So for in-plane MRAM, we said the minimum diameter is around 60 nanometer. Right? We cannot shrink the MRAM to be smaller than 60 nanometer. But perpendicular, materials with a perpendicular anisotropy, they have very large anisotropy values. For example, you take iron platinum, it has the value of 7 times 10 power 7 per cubic centimeter. So if you take a cube of or small diameter of iron platinum, so for diameter as small as 2.6 nanometer, you can make the magnetization of this iron platinum to be thermally stable. Okay, so in this particular case, I don't remember what is the thickness. Okay, but you can calculate what can be the, let's say if your thickness is 2 nanometer, what will be the diameter of iron platinum that can retain the information for 10 years. You can calculate based on the formula KUV by KBT to be 60. Okay, so KU you take from here. Okay, this value is the KU. So you know the thickness, you want to calculate diameter, so the volume is somewhere here. Okay, so you can calculate the diameter based on these numbers. Okay, but right now I am saying it's around 2.6, but for very thin films this may be slightly larger. Okay, so there are many materials like this with a very large anisotropy. So you can use these materials for making perpendicular MRAM. Okay, so with this idea, people have started looking at perpendicular MRAM for many years. Okay, so if you look at this paper, for example, this paper was published in 2002. So in this paper, these researchers have used terbium iron cobalt as a layer that can retain the magnetization in the perpendicular direction. Okay, so this terbium iron cobalt is a material, is an amorphous material. So people have been studying this material for many years, like almost 40-50 years, for application in something called magneto-optic recording. Okay. So this recording technology was popular around 1990 to somewhere 2000, something like this. So when I was doing postdoc, I used to carry this for playing songs. Okay. So those days we don't have like smartphone, so we need to carry some device to play music. Okay. So this is a music player where we insert this disc. So this disc can store songs lasting 74 minutes. Okay, so this disc is called a magneto-optic disc. So I mean, this is a magneto-optic disc for storing information like computer data. So I used to back up my information in this disc, and this is called a mini disc. So we can write songs into this disc and play music. Okay, so this is called magneto-optic recording technology. Okay, so this technology uses this material, and this material can give rise to perpendicular anisotropy. So that means if you grow this terbium iron cobalt on certain substrate, the magnetization will be pointing perpendicular to the disk surface. Okay. So these researchers from Japan, they proposed that we can use them for perpendicular MRAM. Okay. So if you look at this structure, you will see an aluminum oxide. Aluminum oxide is the barrier for tunneling. Then we have free layer. This is the free layer. And one of them is a reference layer. Okay. So you can magnetize this free layer to be parallel or anti-parallel and store bits 0 and 1. Okay, so this is one of the earliest proposals of perpendicular MRAM. Okay, but there are a few problems with this particular technology. First problem is corrosion. Okay, these are, I mean, materials like terbium, erbium, all these materials can easily corrode. Okay. So if you buy a terbium target and keep it in your desk for a few days, you will see that it has become black. Okay. So they can oxidize easily. So this is one of the problem. First problem is that they cannot withstand corrosion. The second problem with this particular technology is like you need to use very thick layers like 13 nanometer terbium iron cobalt, 15 nanometer gadolinium iron cobalt and things like that. So only then you can get PMA. So later you will have writing problem when you have very thick layers. The third problem associated with this material structure is the damping constant. Okay, I haven't explained what is damping constant so far. So next slide I will explain what is damping constant. So I told you that magnetization is the angular momentum. So if you switch the magnetization from one direction to the other direction, it precesses, then finally goes to the other side. So you notice that initially it was in this direction, then when it comes to this direction, it doesn't quickly settle into this position. Okay. So even after it has reached the other direction, it keeps precessing, then finally slowly settling into one particular direction. So you see there are so many precession happening. So for example, I used to carry a ruler. So if you have something if you have a ruler, right, the scale, if you like give a force, then the ruler will vibrate. After some time it will settle, right? So the settling is basically because of the damping of oscillation. So if you have some oscillations and how fast you damp, that's related to the damping constant that we are discussing. Okay, so there are two possibilities. In one possibility it takes very long time, so it goes through so many precession, then finally stops here. So this means low damping. Another possibility is like it comes here, then quickly stops. Okay, so this is like high damping. So if the magnetization settles faster, that means high damping. If the magnetization settles slowly, we have low damping. Okay, so which is better, high damping or low damping? High damping, okay. Anyone says low damping? Okay, depending on what you are looking at. Okay, so if you are looking at the speed of operation, okay, if you are looking at the speed of operation, high damping is better. Because your magnetization was initially in this direction, you apply say spin transfer torque or magnetic field, so this is precessing fast and comes here, settle fast. Okay, so that means we can switch from one direction to the other direction fast. So high damping is good for speed. Okay, so that's what I have written here. High damping is useful for faster reversal. On the other hand, if your damping is high, so what does damping means is the ability to disturb from the initial position. Let's say, okay, let me go back to what we learned yesterday. So when we learnt about spin transfer torque yesterday, let me break this slide. So if you remember the learning yesterday, when we talked about spin transfer torque, I was talking about magnetization making certain angle with respect to the applied field. Okay, so magnetization precesses around the field. Okay, this is something that we learned. Then I also told you that there is some Gilbert damping which forces the magnetization to be parallel to the field. Okay, so damping helps to make the magnetization parallel to the applied field. You can say quickly, in another aspect, we can say that if damping is high, you need more energy to make the magnetization precise. Okay, or even switch information. Okay, so that's the second point. So if your damping is high, you need more current or more field to switch the magnetization. Okay, so there are benefits as well as problems. Okay, damping helps to improve speed, but damping makes the writing current larger. So if you look at the materials that we just discussed, these materials had a high damping constant, which means we need more current to switch this magnetization. Okay, so that's another problem. So they need more energy for writing. Okay, so after this study, not many people studied this material. Then people also started looking at cobalt, palladium, cobalt, platinum multilayers for MRAM applications. So here the interface anisotropy is the one that makes the magnetization perpendicular. And this research was carried out, say, around 2010. So here again the damping constant is large, so you need more writing current. That's one problem. The second problem is that these materials grow with FCC 111 texture, which is not good for magnesium oxide 002. Okay, so tomorrow you will learn that this kind of texture is good for achieving high TMR. So if the materials you grow for MRAM disturb this crystalline formation, then your TMR will be sacrificed. Okay, so this is second problem. So you notice that in all these cobalt palladium multilayers, TMR ratio is very low, around 20 to 70, whereas we are able to get around 200% TMR in current products. Okay, so comparatively you notice that these TMR values are not good. That's because the crystal structure are different. Okay, however, these materials have very large anisotropy field and they are suitable for reference layer. So you cannot use this material for free layer, but you can use this material for reference layer. So towards the end of the day, I'll tell you that these materials are used as the reference layer in perpendicular MRAM. So this is also not very useful as a free layer material. Okay, we cannot use cobalt palladium materials for free layer. Okay, not useful. Then people also looked at iron platinum based MTJs. So I told you that iron platinum has a very large anisotropy constant, so they can support small MRAM sizes about 5 nanometer. So earlier I told you 2.5, that's for a cube I think, but if you make thin films of iron platinum, you can achieve 5 nanometer size using iron platinum MRAM. And the crystal structure of iron platinum also supports the MgO 001, which we discussed earlier. So this also no problem. But again, these materials have very large damping constant and you need a very large writing current to write information. Okay, so writing power is a problem with these MRAM. So you see, people didn't like sit idle. They tried so many materials with perpendicular anisotropy to achieve perpendicular MRAM, but until this point, somewhere in 2010, nothing worked. So all the materials people looked at had some problem or the other. Okay. So I already told you, if alpha is larger, you need a very large writing current. So most of the material that we saw earlier all had very large damping constant. So this is the damping constant. Okay, so because of the writing current, larger writing current, they were not useful. Okay, so you look at all the material that I showed you before: cobalt platinum, cobalt palladium multilayer, all this iron platinum, all this material have very large anisotropy, which is good. I mean, large anisotropy is good because you can make smaller MRAM. But all these large anisotropy material also have large damping constant, which is not good. Okay. So you want to have large anisotropy, but small damping constant. So somewhere here in this circle. So until 2010, we didn't have any material with large anisotropy but small damping constant. Okay. But a breakthrough happened in 2010. So a group from Tohoku University in Japan, the group led by Professor Ono. So they came up with a material which had the desired characteristics. So I told we are looking at some material which have large anisotropy constant but low damping. So I told you we are looking at materials in this area. So the materials proposed by this group in Tohoku by Professor Ono and other people. So they had these properties. Okay. So before I tell you what it is, let's do some questions. Okay, both are correct answer. Perpendicular MRAM materials have high anisotropy constant, so you can make them smaller. Smaller MRAMs are possible with perpendicular MRAM, and they have better writability compared to the in plane because you are not spending extra energy more than the storage energy. Okay. Next question. Okay, most of you are right. This terbium and cobalt has a high damping constant and it has a corrosion problem. So all of the above is the correct answer. Okay, so cobalt palladium multilayers grow in FCC texture, which is not good for MgO, BCC. So they have this poorer TMR problem. They also have large damping constant. So both has to be pressed. I think most of you have done that. Okay, so most of you are right. Okay, here many of you are wrong. Okay, I told you that the iron platinum has a very good lattice matching with respect to magnesium oxide. So the TMR is not affected. Only problem is the higher damping constant. So this is the correct answer, not both. Okay, let's skip this one. Okay, so I told you that all the materials that we had studied before had very large anisotropy constant, but they also had large damping constant. And we were looking for materials with a lower damping constant and large anisotropy field. So in 2010, the group of Professor Ono from Tohoku University, they came up with this material like tantalum, cobalt iron boron, magnesium oxide, which had a perpendicular anisotropy, which had reasonably high values of anisotropy constant and a lower damping constant than any other PMA material that we had. So from here, now we have come to this region. So lower values of damping constant, but reasonably high values of anisotropy constant. They were achieved in this tantalum, cobalt iron boron, magnesium oxide system. Okay. So we can say that this is a boon for the first few generations of STT MRAM. Okay. So once this material was published, there were a lot of interest. Okay. So we know that let's say we have some layer like tantalum, and on top of this we grow cobalt and boron. Let's say if this layer is quite thick, say 3 nanometer or something like that. Okay, so we know that magnetic films will have easy access in the in-plane direction. Okay, so quite for many years people were studying cobalt iron boron based in-plane MRAM. So if you remember a few slides ago, I was showing cobalt iron boron, magnesium oxide, cobalt iron boron, things like that. Okay, so this is not a new material. Okay, cobalt iron boron, magnesium oxide, cobalt iron boron, these are not very new materials. People were using 3 nanometer or 5 nanometer of cobalt iron boron. Okay, and the magnetization was lying in plane, so they were using this as a in plane MRAM material. Okay, so what this group did was shrink this thickness from 3 nanometer to 1 nanometer. Okay, So they were curious, what if we don't make this cobalt and boron very thick, but make them thin? So whether we can get some kind of interface anisotropy, like we get in cobalt platinum multilayers, right? So they wanted to see whether we can get some form of interface anisotropy by making this cobalt and boron very thin. Okay, so that's what they were working on, and that the Tohoku University group and another group from IBM, they worked on this concept almost at the same time. And here I am showing the results from IBM group. Okay, so here you notice this is cobalt and boron thickness. So this cobalt and boron was deposited either on tantalum seed. Blue is the tantalum seed. That means on top of tantalum layer they are growing the cobalt and boron magnesium oxide. And this red color is on top of ruthenium. Okay, so ruthenium, okay, I also have to explain what does this mean. So when you say Ku, so positive Ku means the magnetization is perpendicular to the disk surface, I mean wafer surface. When we talk about negative Ku, it means magnetization is in the plane. Okay, so that's what is shown here. So here you see is positive. So above this line Ku is positive, which means magnetization is perpendicular. Below this line Ku is negative, which means magnetization is in plane. Okay, so this is the cutoff line. So when you grow cobalt and boron on top of ruthenium, Ku is always negative. So even if you make the cobalt and boron thinner, Ku is always negative, which means magnetization is lying in plane. Okay, on the other hand, let's say we grow cobalt and boron on top of tantalum, shown by the blue dots. Ku is negative until this point, which means magnetization is in plane. And when you go to about 1 nanometer, you see the Ku becomes positive. So in this region, you can see Ku is positive, which means for this range of thickness, magnetization can lie perpendicular to the disk surface. Okay, so this is the observation from IBM, and the group of Tohoku also have similar observation, which I will explain using this graphs. Okay, let me zoom in the graphs. Okay, these are too small. Let me get this one. Okay, for you this task may be easy, but I am spending more time. There is a reason, I will explain later. Okay. Okay, now we look at the results from Tohoku University. So here they plot the hysteresis loop of the sample with the cobalt and boron thickness of 1.3 nanometer and 2 nanometer. Okay, so red means the magnetization is, let's say this is your sample. They apply magnetic field either in the perpendicular direction or apply magnetic field in the plane direction, and they measure two hysteresis loops. Okay, blue is actually this one. Let me use the color code, correct color code. Blue means magnetization is applied in the parallel direction. Okay, so when magnetization, the thickness is 2 nanometer, this is the EZ direction, right? So EZ direction has larger remnants, it saturates quickly. So EZ direction is in plane, and the other direction is hard. On the other hand, when they reduce the thickness of cobalt and boron to 1.3 nanometer, you notice that the perpendicular direction is the EZ direction because it saturates quickly and it has larger remnants. So we learned this before. EZ direction, we have larger remnants, we can saturate quickly, and the blue direction is the hard direction. So perpendicular direction is the EZ direction and in plane direction is the hard direction. Okay. So that means if you make tantalum, cobalt and boron, magnesium oxide, and if this layer is very thin, for example around 1 nanometer, then the magnetization of this layer is going to be perpendicular. Okay. For the same structure, if you make a tantalum, cobalt and boron, magnesium oxide, and if this layer is like 2 nanometer, for example, it's going to be in plane. Okay, so just by changing the thickness of this layer, they have produced some interface anisotropy, okay, which leads to the perpendicular anisotropy. Okay, so the beauty of this material is that its damping constant is very similar to the cobalt and boron which we use for in plane application. So damping constant wise no big difference. Okay. So but it can have very large anisotropy. So it can make the magnetization perpendicular. Okay, so there is some reason why the interface anisotropy is observed. So people say that it's due to the hybridization. Let's not go into the details. Let's come back to the results of Tohoku University. So here they study many different properties like what is the anisotropy field. So you have learnt that anisotropy field is the 2Ku over Ms. So anisotropy field, then damping constant, and the tunneling magnetoresistance, all these properties they study as a function of thickness of the cobalt and boron. Okay, so when the thickness is very large, say 2 nanometer or above, this value is small, negative, but when you go towards smaller thickness, you see large anisotropy field, positive anisotropy field, which makes the magnetization perpendicular. Here is in plane. And you will notice that when you reduce the cobalt and boron thickness, alpha increases. Okay, it looks very large here, but still this alpha is much lower than the damping constant of 0.1 that we saw in other materials before. Okay, so we saw so many other perpendicular magnetic material which had alpha of 0.1, but this material still has a lower damping constant, which means you don't spend too much energy to write information on this material. Okay, and this material also supports high TMR ratio. So in this graph you will see that this material doesn't spoil the TMR ratio. It's still as high as 100%. This was okay. Okay, but now people have made this to be like even 200%. So all these results indicate the potential use of this material. So anisotropy is high, damping constant is not a problem, all those things. Okay, and this group showed that you can make MRAM as small as 40 nanometer. So this number is 40 nanometer, and you can achieve MRAM property. So from this study they showed that in plane MRAM can be only shrink to 60 nanometer, but if you use this material, tantalum, cobalt iron boron, magnesium oxide, you can bring this down to around 40 nanometer. Okay, so after this paper was published in 2010, many companies started making MRAM, and now it's a product. Okay. Okay, let's do some questions. So this kind of PMA that I have described so far is called interface PMA. Okay, IPMA. We use this term IPMA for this particular form of perpendicular magnetic anisotropy. Okay, so this particular thing is scalable to 35 nanometer, and it's also easier to manufacture. Okay, so the correct answer is all of the above. Okay, next question. The interface PMA depends on Okay, so I didn't teach you this clearly, so wrong answers are okay. The correct answer is all of the above. Okay. So if you remember the discussion we had, I showed you two data from IBM. In one case they used tantalum below cobalt iron boron, in another case they used ruthenium below the cobalt iron boron. So in the case of ruthenium, there was no perpendicular magnetic anisotropy. Only the tantalum seed layer gave rise to the perpendicular magnetic anisotropy. Okay, so seed layer plays an important role. Of course, you all know that the thickness of cobalt iron boron layer plays an important role. I didn't teach you that this oxide layer also plays an important role. It was in the slide where we discuss about the origin of PMA, the hybridization. So all this depend on oxide layer. Okay. So when this work was published, I asked my student to try tantalum, cobalt iron boron multilayer to see whether she can get perpendicular anisotropy. Okay, but we didn't get. Okay, so this implies that this oxide layer also plays an important role. So all these are important. So you need a tantalum or some suitable seed layer, and you need a thin cobalt iron boron. This is important. You also need magnesium oxide. All these three layers play an important role. So the correct answer is 4. Okay, so now let's move on to the next design. So first design is IPMA. So we have interface PMA. Okay, people are not happy with what they have, right? So from 60 nanometer in plane MRAM, you can bring down to 40 nanometer MRAM based on the interface PMA concept. But the technology has to grow better, right? So we want to make even smaller. From 40 nanometer MRAM, can we shrink down to say 28 nanometer or something like that? Okay. So people always try to improve the technology. That's where the researchers come in, right? So for this particular concept, we cannot increase the thickness. So in the interface PMA, you cannot increase the thickness. So we know that KUV is the anisotropy constant, right? So if you increase the thickness, you can increase volume. But in the case of interface PMA, you know that if you increase the thickness of cobalt iron boron, magnetization will go from perpendicular direction to in plane. So you cannot just increase the thickness of cobalt iron boron. Okay, but if you want to increase the volume of the device, you can come up with some creative idea like this. Okay, so instead of having one tantalum layer and one magnesium oxide and one cobalt iron boron, this configuration smartly introduces two interfaces of tantalum, cobalt iron boron, magnesium oxide. By introducing one tantalum layer in the center, okay, we have one tantalum layer here, two cobalt iron boron layers, and we have two magnesium oxide layers. Okay. Okay, so this is the normal IPMA interface. You have tantalum, cobalt iron boron, magnesium oxide. Whereas in the dual IPMA structure, you have only one tantalum which is in the center. Then if you look at this way, you have a tantalum, cobalt iron boron, magnesium oxide. If you look from here, you have another tantalum, cobalt iron boron, magnesium oxide. Okay, so now you have two magnesium oxide layers. Basically, you are now doubling the volume, right? So you have two layers storing information. So you can basically double the volume. So that is the idea of this dual perpendicular magnetic tunnel junction. Okay, so with this particular concept, people can achieve 28 nanometer diameter MRAM. Okay, so because you have increased the volume, now you have two layers, so your thermal stability is increased. And people also found that for same writing current, thermal stability is higher. Okay, that's one thing. Then one fine aspect of this particular design is when you read information, these three layers play an important role. Okay, so here you need to have optimum thickness of magnesium oxide for achieving high TMR. Okay, but here you can make very thin magnesium oxide because here you are just creating an interface to get perpendicular magnetic anisotropy. So for the bottom side, they will use thinner magnesium oxide. Okay, because here your magnesium oxide is not useful for reading. You just want to have this interface to get perpendicular magnetic anisotropy. So they make the MgO thinner. Okay, so these are the fine aspects of this particular design. Any question? So what magnetic material you suggest besides cobalt and boron? You tell me, Moditma. Writing energy being more in plane MRAM compared to perpendicular MRAM with respect to the difference between HP and HK. Okay, I'll come to that. But Moditma, answer my question. What other material you want other than cobalt and boron?
So this boron is basically very small and non-magnetic.
Yeah.
So is it kind of a doping only?
Yeah, it's a doping, yes.
So should it will can give a secondary phase in the gate one?
Okay, this cobalt iron boron, when you sputter, it is amorphous. Okay, so when you make MRAM, this cobalt iron boron is deposited as an amorphous layer, but in the MRAM process, they will do some annealing. Okay, after they deposit all these layers, they will do some annealing at around 300 degrees Celsius. So during this annealing, this this boron will go somewhere to the tantalum layer or some other layer. So boron will diffuse. So you will have a crystalline cobalt iron layer. Okay. So the final result is the cobalt iron crystal. Boron will diffuse. So why not iron, cobalt, or other magnetic alloys? So what?
I think we answered the question.
Okay. Okay. So today I presented a very coherent story of people looking at many different materials, then finally arriving at iron, cobalt, boron. Okay. So I told you cobalt platinum has problem, terbium iron cobalt has problem, iron platinum has problem. Then I told you why cobalt iron boron is interesting, why it is useful. Okay. So this question shouldn't come. Okay. So people look at various materials based on their properties, then they finally arrive at cobalt iron boron. So I told you a coherent story today. Okay, that's my answer. What is the other question?
To re-explain
okay, between HP and HK. When we are talking about in-plane materials, in-plane MRAM materials, so their anisotropy field is very low. Okay, their anisotropy field is around 50 worsted or 100 worsted. Okay, but if you look at the field, the perpendicular, I mean the field you need to keep the magnetization in the perpendicular direction, that field can be like 10,000 worsted, something like that. Okay, so I told you during the precession motion of magnetization going from one side to the other direction, so the precession happen, then the magnetization is spending a long time in the perpendicular direction, which means we need to apply this field for quite large number of time. Okay, so you see the difference. Anisotropy field is only 100 worsted and you are applying 10,000 worsted kind of field to switch. Okay, so this is the difference. So your HK and HP are quite different in plane MRAM materials. Okay, on the other hand, in the case of perpendicular material, the HK is around, let's say 5,000 or 10,000 worsted. So this is the field that helps to retain information, retain or store information. Okay. Okay, so in this case, when you switch magnetization, so I told you this is like a Stonor-Woolford particle. So this is HK, right? So easy direction is perpendicular, hard direction is in plane. So even if your magnetization is going from perpendicular to one direction to the other direction through the in-plane direction, basically the hard direction field is same as HK in this case. Okay, so you don't spend extra energy to switch information.
In this scenario, how will be the energy barrier for the two in plane and out of plane? Which one will have a higher energy barrier?
I mean, so when you are talking about this, right, what does the energy barrier mean? So say you have in plane, I mean, okay, sorry, let me redraw this. So when we draw the energy barrier diagram, what is your y-axis? Sorry, x-axis.
Maybe the angle.
Yeah, so it's the angle, right? So let's say this is one easy direction, this is other easy direction. So this is the energy at a hard direction. Okay, so hard direction, the energy is high, it's not stable. So energy barrier is basically this, right? So you cannot talk about energy barrier in the hard direction. Hard direction, there is no energy barrier. It's at the highest energy.
Yes, but in out of plane configuration,
Mm-hmm.
we are having an energy barrier, and in plane configuration we will also have energy barrier.
Yeah.
I just want to know which one is the higher energy barrier.
Okay, so you are comparing between this and this, right? So this is what I mentioned a few minutes ago. So this case, okay, if you convert this into HK, okay, which is 2 KU over MS. So this, in terms of field value, this can be like 10,000 Oersted. Okay. In the case of in plane material, this HK is only around 100 Oersted. Okay, so it's much low. Okay, now let's move on to the last concept. Okay, so for in plane we had 60 nanometer limit. In plane 60 nanometer limit. Then for the IPMA we had like 35 nanometer limit. Then with the dual IPMA we had like 28 nanometer kind of diameter. So people are looking at whether we can go even below 28 nanometer. Okay, so in that connection they proposed a concept called nano MTJ. Okay, so this nano MTJ combines two anisotropy. Okay, one is the shape anisotropy plus the interface anisotropy. Okay, this nano MTJ makes use of both shape and interface anisotropy. Okay, so if you look at the sample here, so they have some kind of tantalum kind of layer, then a ferromagnetic layer and a magnesium oxide. Okay, but this layer is very thick. Okay, so around 15 nanometer. Okay, so this layer, we know that when the magnetic layer is very thick, magnetization has to be in plane. Okay, so if you grow a film like this layer will have in plane magnetization. But in this study, what they have done is they made lithography in such a way that they can make a kind of cylinder. Okay, so we know that when we have a cylinder, the z-axis is in the perpendicular direction, I mean along the length direction. So because they made this so small, because of the shape anisotropy, this magnetization is now pointing in the up direction. Okay, so this is called nano MTJ because they are making MRAM devices now in the 5 nanometer, 10 nanometer kind of range. So this is called nano MTJ. Here because of the shape anisotropy, so you see that this is like a perpendicular, cylindrical shape, right? Because of this shape, the magnetization is in the perpendicular direction. Okay, so this is again from Tohoku University. So they measure hysteresis loop in the perpendicular direction. Then they observe perpendicular hysteresis loop for 4 nanometer diameter, 7 nanometer, 11, 15. All these small diameters they can observe perpendicular hysteresis loop. And in MRAM community they use the symbol delta to represent KUV by KBT, thermal stability. So when you see delta is around 80, what it means is that KUV by KBT is around 80, which means data can be stored for around 10 years, more than 10 years. Okay, so now the next step to go below 28 nanometer, for example, even 4 nanometer MRAM can be achieved using this nano MTJ design. Okay, let's do some questions. Okay, majority of you are wrong. So two interfaces of cobalt and boron will look something like this, right? Can this give PMA? It cannot, okay? So this is wrong. We need this, everything. I told you that seed layer is important, magnesium oxide is important, and this being thinner is also important. All these are important. So this is the correct answer. This or this are wrong answer. Okay, let's skip this one. Let's go to the last slide. Okay, so far we have been only learning about the free layers. So the free layer can be tantalum, cobalt and boron, magnesium oxide, or it can be a dual PMTJ. So we have been focusing only on this layer, but I haven't told you how the whole stack of MRAM will look like. Okay, so the free layer is at the top in this particular design. Okay, then we have some magnesium oxide. Okay, then this whole thing starting from that blue layer on top all the way here is called the reference layer. Okay, so you notice that there is a thin cobalt and boron layer at the top. The reason I'll explain later. Okay, there is a thin cobalt and boron at the top, which I'll explain tomorrow. Okay. So today you just take this for granted. The main aspect of the reference layer is this cobalt platinum multilayer in the synthetic antiferromagnetic structure. Okay, so we learnt about this synthetic antiferromagnetic structure. The two magnetizations are pointing in antiparallel direction. So this helps to reduce stray magnetic field from the reference layer. Okay, so in the perpendicular MRAM technology, we are using cobalt platinum multilayers as the reference layer material. Okay, so these multilayers have a very large anisotropy field or anisotropy constant. So the HK of these materials can be as high as 20,000 Oersted. So during the read or write operation, this magnetization won't be switched. Okay, so the reference layer magnetization is always fixed. Fixed because of the high anisotropy. Okay, these materials have very large anisotropy, We don't need to switch them during the reading or writing operation. So they are always fixed. Okay, so that's why we use cobalt platinum multilayers. Okay, so this is how the reference layer will look like. And to induce this synthetic antiferromagnetism, people use either ruthenium or iridium. Okay, so this is the last slide. Any questions? Okay, if you think we are learning too many things, it's better you watch the YouTube video at night. Okay, so YouTube videos are streamed every day, right? So today's video will be available in a few minutes. So at night you go through the recording. Otherwise, like too much information, all may be going above your head. Okay, so please watch and reinforce the concepts. Yeah. Okay.
Practically doing this big structure, how are they done? I mean, in single sputtering system, all these many targets are put on.
Okay.
I mean, a number of layers.
Yeah. So the industry sputtering system usually will have a few chambers, at least 2 chambers. Okay. Some machine may have 3 chambers. So usually they will have 1 chamber for oxide deposition. For example, magnesium oxide you want to deposit. So there will be a dedicated chamber where you deposit magnesium oxide. Let's say you deposit cobalt, platinum, cobalt and boron, and say tantalum. So there will be 1 chamber for such targets. So what happens during the fabrication of this whole stack? So let's say we start with the tantalum. So tantalum will be sputtered. Then cobalt gets, the wafer will move from this place to this place. Cobalt will be sputtered. Then next layer platinum. So the wafer will move to platinum. It will get sputtered. Then it will come back to cobalt. So there will be a lot of back and forth oscillation. So many of these multilayers will be sputtered. And let's say we have ruthenium here. So when you want to deposit ruthenium, the wafer will move here, ruthenium will be deposited, and so on. So after everything until here is deposited, then this wafer will move to the magnesium oxide chamber. Magnesium oxide will get deposited, then it will come back, then the remaining layers will be deposited. So it's like, so there will be 2 or 3 chambers to answer your question. Yes. And this transfer all happen in vacuum. Okay, so when it goes from this side to the other side, vacuum is not broken. So the chambers will have base pressures of 10 power minus 8 or minus 9 torr. So wafer doesn't come out until everything is finished. All the layers must be sputtered, only then the wafer comes out. Any other questions? No. Okay.
Hello, sir.
Yeah.
So, what could be the ratio of the MGO thickness and dual PMTJ?
Okay, the ratio of the MGO thickness in dual MTJ. Sorry. So you are talking about this one, is it? So in the case of TMR, right, when you want to read information, we design MgO thickness to be around 1 nanometer, maybe plus or minus 0.2 nanometer, you can say. So this is the thickness of magnesium oxide here. So here, if you make the magnesium oxide too thin, you may have pinholes. So some region magnesium oxide may not be sputtered, so you will have pinhole, there will be no tunneling, so TMR will be affected. So to ensure that you have reasonable TMR, the magnesium oxide here will be around 1 nanometer. But in this, at this position, you don't need to make that magnesium oxide very thick. So maybe it's around 0.6 nanometer or 5 nanometer. I don't know the exact value, but I am just guessing that it could be around 0.6 nanometer.
Sir, I have one more question.
Mhm.
Recent research on dual TMT gate, they tell that thinner top MgO barrier is used and thicker bottom MgO barrier is used for a PMT gate in order to maintain the PMA and TMI. So, how is that feasible?
Okay, whether it's bottom or top, it depends on how you design your MRAM. So in this particular case, my free layer is at the bottom. Okay, reference layer is at the top. So in that case, this layer has to be thicker. But if they design with the free layer on top, reference layer at the bottom, right, then this MgO has to be thick. Okay, so don't use the terminology like bottom magnesium oxide, top magnesium oxide. Just refer to the magnesium oxide that's at the interface between free layer and reference layer. Yeah.
Thank you, sir.
Okay, thank you. Okay, if there are no questions, we end here. Thank you.